Welcome. We are hoping that you're having a great time at reInvent. It's Monday, so I think it's the first day, so there's a lot more to go. Today, we're going to talk about two important things. The first is healthcare, patient data, which is the central theme of all that we do when we talk about healthcare analysis and BI. And the second thing is that what it takes us to create a process or a system where you can easily create analytics, where you can easily write machine learning models, where you can easily write data, descriptive, predictive, prescriptive, you name it, any kind of analysis. What it takes to create a system that can drive interventions, what it takes to create a system that helps, empowers the end user to create a system which can then be utilized to create models for data intervention. So before we dive into the creation of this process or the services or anything like that, let me highlight a few points. And I'm sure you all are expert here in this room, and this is maybe something which is redundant, but I just want to take a quick moment to talk about the power of healthcare BI. Forecasting a chronic condition, okay? You have a set of people who have diabetes. You want to predict their kidney failures. You want to predict congestive heart failures on patients. Descriptive analytics, this is what we do, basic, average, min, max, sum, standard deviations, and other things. Deep learning using medical images, this is something that, getting more and more important. Somebody told me the other day that, hey, I want to take a picture of your heart, but not from outside, inside, X-ray that is. And want to run some deep learning models to extract the features. And what does it mean? It means that I want to study the images of your heart to find out what is the best treatment for you if you're suffering from a chronic condition. Okay? So again, part of analysis. Optimization of an EMR workflow. And and EMR, this is not Amazon EMR, this is Electronic Medical Record System, or EHR. In hospitals, we use this EMR system for labs, for medications, for encounters, right? And our clinicians and our physicians and nurses and all that stuff, they use this system, EMR systems, for majority part of the day when they're not treating patients, okay? So how to optimize this is also part of analysis. And then interventions. It is a continuous cycle, right? So we start with finding out the patients who needs a treatment or we want to forecast certain diseases. Well, once you find that out, what do you do next? You provide interventions. So what are the main challenges that one sees when you're creating a system, a healthcare BI solution? The first one is the infrastructure, right? So I have a 60 terabyte database, or I have 55 terabyte database, or I may have even 100 gigabyte of database. Sometimes, and most of the times, actually, it is not an easy process for me to procure this set of hardware, which can actually scale with my needs. So today, I may have 200 patients. Tomorrow, I may have 20 million patients, okay? The infrastructure has to scale with the need. The second challenge that we have in healthcare BI is complex and noisy data. So data is always not friendly. It comes from, I mentioned, from the EMR systems. It may come from a glucometer. It may come from a weighing scale. It may come from any other sensory devices that you have in your home. And the third thing is usability and adoption. Now, why do I put it out here? Is because if I'm a data scientist, or if I'm someone who is doing the data analysis, if you give me an infrastructure, great. If you solve my data problem, perfect. But you still need to give me a system where I can go and easily create my models. I can easily share my model. Remember, we talked about interventions before? Something that we can drive, something that can help us drive the intervention. So the first challenge, the infrastructure. We have multiple data sources. We have data from EMR. We have data from labs, medications, encounters, you name it. Various data models coming from various sources. You may end up having different data models. As simple as you take a blood sample from your glucometer device, the data, the streams that back to the data source is obviously different than an encounter information that we have. Data transfer rate. Now, if I'm a data scientist, data analyst or somebody like that, for me to log into your database and run queries and get the data out of that and then put that in a machine learning system, you call it Spark or or Hadoop or anything for that matter, you need to transfer the data back and forth between these systems. Elasticity, with my needs, with the number of patients, with an epidemic, or with anything that requires for me to scale out or to scale back in, something that is also a challenge. So these are first of the 3 challenges we talked about. The second one is the complex and noisy data, which I touched upon briefly. And the third is the usability and adoption challenge. And now I want to make sure that we all in this room understand what we mean by usability and adoption when we talk about that. First of all, you gave me a system, an infrastructure, where I can connect. So that's good, okay? What are my permissions? What are the drivers I'm supposed to be using? What am I networking? How am I encrypting this data? The second is that how do I share? So I built a cool model on sepsis or congestive heart failure or anything for that matter. But once I'm done with my model, how do I share my work with others in my organization, or even better, to the intervention team, which is actually going to drive this intervention, take it forward? How do I reuse my research? So you spend close to 6 months in generating a model, feature exploration, and all that. You don't want that work to just get wasted. You want to reuse that work over and over again. How do I find new packages? Now, if you have worked with any Jupyter notebook-like package or any machine learning, you will recognize this, that as and when I use new research, I escalate my findings. I need to get to new packages, and we'll talk about that in detail when we have our speaker. How do I package? Now my work is done. I want to package my work so that others can use it. So starting from finding the data to resolving the infrastructure to creating a system that can actually be leveraged, for better patient care, because that's the central theme that we're all working towards. Okay. Now, the first aspect is the infrastructure and the data, right? So one thing that we can do, and that one thing we want to emphasize in our today's discussion, is using Amazon S3 as a data lake. Now, what is a data lake, right? So data lake is something that where you collect data from multiple sources. You create a system where your analysis can sit on top of it, as opposed to going to multiple data sources and connecting them from your application. So something as an example here is trading on-premises SDFS for durability and scalability with Amazon S3 in the cloud. And these slides right now that I'm presenting are at a high level. We're going to have our speaker who's going to go much in detail on all of these options, including Amazon S3 as a data lake. So now I have my data consolidated. I have my data from different sources. I created a data lake. Why do I need Amazon S3? Well, if you look at this picture, on the left-hand side, you have data from different ERP systems, weblogs, connected devices, social media, EMR systems, glucometers, sensory devices, IoT, and whatnot. And then you scale it. You put the data in one place, Amazon S3, ingest that, and then from there, either you can direct query the data using Amazon Athena, which is our query engine, which you can directly use it against S3, or you can scale it. You can use Amazon EMR. It is the use case we're going to talk about today. But Amazon EMR is a Hadoop framework where you can run on Amazon, where you can run Spark jobs for advanced data analysis. So you can see in this picture that how can I take data from multiple sources, ingest into S3, and actually utilize that and leverage that information across multiple channels. EMR. So EMR, like I said, is a managed Hadoop framework that makes it easy, fast, and cost-effective process to process vast amounts of data. So if you worked with Hadoop framework before, this is a framework which is fully managed by Amazon on a cloud. As you can see in this diagram, we have an Amazon EMR sitting on top of multiple sources. Amazon S3 is one of them, and that is where we just built our data lake. Now, with the data, now we have the data. We have an engine that can process it at a big data scale. The next thing comes encryption. So Amazon S3 provides data at rest encryption. You can directly encrypt your data in S3. Then Hadoop, I mentioned that. SDFS, data transfer protocol. So data in rest as well as data in transit. Both of these encryption can be achieved by the managed services that we have. MapReduce, SSL for encrypted shuffle, and finally Spark, in case you're using Spark, and that's one of the examples we have today. We can use SSL for block transfer services among the others. So the encryption is done, data is in the data lake, We have used big data analysis platform like Amazon EMR to perform analysis. So some part of our problem is kind of resolved. The next thing is the monitoring. Okay, so how do I know who's accessing my data in S3? So for that, we have bucket access logs. In EMR, you can archive various log files that eventually go to CloudWatch and generate metrics every 5 minutes. So now we have a cycle which is connected from the source system all the way to the monitoring. Now, remember, I also talked about complex and noisy data. I also talk about the usability and adoption. Okay, so to go deeper into that, I would like to call upon the speaker from Cerner. So Cerner is one organization that I've seen as continuously building on the foundation of intelligent solutions. Its technologies connect people and services more than 27,000 facilities worldwide. Cerner is creating a future where healthcare systems works to improve for the well-being of patients. They're always on the cutting edge. And from Cerner, I would like to invite Ryan Brush, who's a principal architect at Cerner. He created Clara, an open source engine for rules. He is deeply involved with data engineering analysis and the application at a very large scale. And I'm working with Ryan for a number of months now. And I've learned so much from him in all these months that I couldn't even think about it before. He's a renowned speaker. He spoke at multiple conferences, and he co-authored some chapters in those books, 97 Things Every Programmer Should Know, and Hadoop, the Definite Guide. So with that, I would like to call upon Ryan Brush from Cerner.
All right. Thanks, Navneet. I think you were trying to make me blush a little bit there with that overview, but I appreciate it. All right, so we're going to start with take a quick look at the story so far. And if we could fit everything that we're doing in all of our healthy intent efforts onto one slide, it might look something like this, in that we're bringing together a broad set of almost anything that is relevant in healthcare. We're going through a number of steps to normalize it and put it into some standard structures that we can use. Once we have it in those standard structures, we're applying a variety of analytics, a variety of intelligence to that system. And then we're driving that back into the point of care, back where the clinicians, back where the health coaches, back where administrators of hospitals can apply this value. And a lot of this is happening today on our own data centers. But we're going to talk about how we're continuing to make it better with doing some of the things with AWS as well. And this is a big, complicated system. So we have hundreds of connections to disparate data sources. We have more than 100 million unique person lives in this system. We have several petabytes of data, and these numbers are always going up. We have many different measures and a whole bunch of deep ontologies to work with this healthcare data. And of course, all of this is built upon security, which an area in which we can make zero compromises. So this is what we're doing today, but in the purpose of this talk, we're going to zoom in on a certain piece of this. And then how do we make these efforts, how do we make them smarter, how do we make them better, and how do we continuously improve them? So we'll zoom in on one piece. So we'll take everything that we have in terms of this healthcare data, this enormously vast, complex set of data that we're working with. We're bringing it through this longitudinal record of everything into an environment that data scientists want to use. We want to create something that people want to go to in order to make these things smarter. We want to take that new knowledge and push it into a content management system. So as we have new algorithms that we want to apply, we need to be able to manage it, and we need to be able to bring in third-party content as well. And then finally, of course, we need to be able to push that back into the original healthcare system that we started with. So I am an engineer by background. And so my initial impulse is to take everything we've done and just dive deep into all the technical details of all the complexity that we're dealing with to build this type of system. But really, the purpose of this is not to dive deep into the technical details of it, although we will touch on that as we go. But really, the end goal is, for our users, we really want to make the technology disappear. And when we talk to our users, we talk to people that you might consider a data scientist or an analyst, and think about the environment that we want to bring to them. Instead of technology, we want to bring them an SQL view of the data. It's accessible, has a very large audience, it's easy to use. Like, bring the data through a familiar SQL interface. We want to be able to do deep descriptive and predictive statistics across that data set. And then we want to be able to write pieces of code to sort of glue these things together, to orchestrate them, to make it happen. I mean, this is the world that we want our data scientists to view, rather than all the complexity underneath that. And so we give them an interface. And so here we have a Jupyter notebook interface where you can explore and manipulate the data. And while they work with this, our challenge that we have from a technology perspective is satisfying all the complexity we talked about earlier. So things like we're working with many petabytes of data at a time. We're working with a number of standard healthcare models. We want all our data to be cataloged, so it's just discoverable. If I have to go and track down what data is there and what data isn't there, or if I had to go pick up the phone and say, hey, where do I get this data set? That takes us out of this sort of innovative loop that we want to be into. I mean, everything that we have rights to should be securely available and should just be there. And then similarly, when we produce new outputs from these either new machine learning models or new views of the data for analysis, we want it to be collaborative so we can publish it back into our data catalog so others continue to use it. We need a rich ontology support. So if you've worked in healthcare, you know there's so many different ontologies that all have a variety of needs and variety of use cases. We want to make that as easy as we can and make it a sort of a native feature in terms of our deep data science environment. And we want to make it extensible. So Navneet mentioned bringing in new packages, bringing in new modules to work with it. We want people to bring in their own approaches to do deep learning, to do analysis of these systems. And of course, it needs to be secure, which is a theme that we'll come back to a few times. So how do we go about building this type of system? Imagine we have this blank page, and how can we go about doing it? Well, one approach that I think that we took early on in this is we went back to one of the classics of software engineering, and Fred Brooks' No Silver Bullet, in which Brooks described there's the essential problem. These are things our users really care about, what's inherent in the problem we're trying to solve. And then there's the accidental problem. So we talked about the essence before, right? We want to have this rich catalog of data set where everything is just there, where they can just work with it. But we have a lot of accidents in this type of system, accidents in the sense of what Brooks means. It's like anything that's not essential to the problem. So things like, hey, we want to work with our Spark cluster. We have a huge amount of metadata. We have provisioning and storage and connectivity and auditing and security, and this list goes on, and all of these are important. If any one of these doesn't work, then our system doesn't work. So we need to approach this. And maybe we do this, I mean, the way that we might have done this historically is like, how do we go about and solve these problems? I mean, maybe what I do is we go and I put on my software architect hat, right? And I go, yeah, all right, I'm going to go through and I'm going to figure out the architecture to solve all these problems. I'm going to do it up front. I'm going to write a glorious white paper. I'm going to hand it off to the engineers, and I'm going to, So that may be what we've done historically. And this approach we can take in an AWS-style environment because there are so many great building blocks in order to assemble the architecture for these things, and that we can glue together. And we can declare, hey, we need this, and bring it in part of our system. But I think that we have an opportunity, working through this type of system to do something better than we might have done historically. I mean, typically we think of software architecture as something that we do up front and we get it nailed down. My favorite definition of software architecture is it's the things that are hard to change in the system, which, as Martin Fowler points out, why are we making things in the system that are hard to change? And in fact, there's no theoretical reason why anything in software has to be hard to change that. So can we do better as opposed to an upfront architecture approach? Can we do something that adapt it much more quickly? So we went about this, rather than doing this massive, big, upfront, let's figure everything out, let's figure out the constraints. Let's figure out the things that we really care about when building our data-driven, our data-centric system. We got to get those nailed down, because there's certain things that are immutable, that we cannot change. But once we have defined those hard constraints, what are the things that are really important to us? We want to optimize for fast iteration, so we're continuously improving the system, continuously making it better. So what are the hard constraints that we would hear? And we'll talk about what they are and how we can satisfy them using this sort of cloud-based stack. Well, the first one, security. And Navneet mentioned a few of these things. Everything is encrypted in flight and at rest. Everything is using a HIPAA-compliant system. We have auditing that goes through and makes sure that everything is compliant with our processes and our policies. So security does not move. That's one of the things that we really care about. We also care about the user experience. We want that sort of magical environment in which if I'm a data scientist, everything that I want to do my job is just there without having to pick up the phone and code everything. And I don't have to go requisition new clusters, everything like that. Everything I want is there for that need. And then I think the third one maybe stands out a little bit. It's a little bit different than the other ones. It's reproducibility. So let's focus on that, just because, yeah, maybe this one seems a little bit different. But I think this is as important a property as anything that we have in this system. And by reproducibility, it's really a simple idea. And it's really that the same input produces the same output every single time. And so if I'm doing a machine learning use case, the same query, I need to be able to recreate that every time I do it in order to tune my models or reproduce previous results to make sure that they're valid. This is important from a user experience use case. It's important from a data engineering use case in which whether using literal Amazon AWS Lambda functions or whether using the computer science Lambda functions to transform data in the more abstract sense, the same input should produce the same output every time. And by doing that, this kind of gets us in a nice feedback loop in which we can kind of continuously be improving the system, making little tweaks, and then changing it as we go. And we'll come back to that reproducibility theme. So with these things that we import, let's go through our architecture. So a lot of times you'll see architecture diagrams sort of grow from the bottom up. But again, I think that this sort of takes away from that way that we think about the system. We wanted to start with what's the experience that our users wanted. We wanted to create that system, and then let's figure out what the architecture is to support that, as opposed to describing the architecture from the bottom up and the user is something that sits at the end. So we start with that user experience at forefront of mind. We know that we also need a way to process, we need some sort of processing engine to do this machine learning, to do these heavy analytics that we're working with in this system. And of course, we needed a way to store the data, and we need metadata associated with it. And so this is, in a way, this architecture somewhat designed itself, because, we obviously need these things. Now our challenge is how do we map them onto the best available tools and then iterate quickly to improve the system as we go. So again, we'll start at the top where our users are. These Jupyter notebooks. So if you've done data science work or worked with data scientists, this is a pretty popular tool in which they can interactively run code and do analytics. We'll show some examples of that. So this is where our users want it to be. In terms of the processing engine, Apache Spark really has a pretty strong mind share when it comes to data engineering at scale. It has a number of the advantages of a MapReduce type framework in terms of it can handle really sophisticated workloads. But it also has a fairly easy-to-use interface in that you can work with it with an SQL interface similar to what we had shown in the earlier slides. And then the storage, it's pretty clear if we're running in Amazon that we're storing things in S3. And with the one exception of some additional metadata for workloads that don't map directly to S3 operations, we store things in a data catalog that is just an RDBMS instance. So that's our first pass through the architecture, but everything we do is iterative, right? So our next pass. So we're using Jupyter Hub running on Amazon EC2, and we're spawning sessions as Docker spawners, which has some nice properties because since every interactive data science session runs in its own Docker container, we can bring their own libraries so they're isolated from the rest of it. So if I have some specialized machine learning need, I can import that library into my container and not affect others. And then everything that we do in here, we store all our long-lived content back into S3, and we'll go into some reasons why in a couple slides. For our processing clusters, we're using Elastic MapReduce. Pretty clear choice. And the other nice thing is that we tend to use a very transient workload. Based on these deep analytic needs, it's uneven in that most data scientists will work during the day and work much less at night. So we actually have a pattern in which we'll spin up a few dozen nodes like during the day or more, depending on the workload. And then at the end of the day, we'll give them back, shut down the cluster to give them back in. And this is actually a really cost-effective way to do things if you have very transient workloads. And at the bottom there's like everything that we store in S3 in terms of we use Parquet-based data, all of our user folders, all of our logs, anything that lives a long time is stored in S3 or in this catalog, which is just a Hive metastore, if you're familiar with the Spark stack. So this is our stack. This is the highest level view of our architecture. But I think that there's one other interesting property that we see as we go through these things, and that in the stack, there's a difference between everything above that checkered line and everything below it. And above the line, we see things that everything is stateless beyond a user session. And everything below that line has some long-lived state that goes in it. And so we found ourselves, our architecture kind of naturally evolved into this area where there's these two distinct worlds. We have our stateful system and we have our stateless system, which kind of led to some really interesting things that we could do to continuously improve the system. So one of which is, for state, anything that lasts longer than a session, we consider stateful. But stateless, we can discard and upgrade. It was kind of neat, right? So if I want to upgrade anything on our stateless stack, I don't have to worry about doing change sets or anything like that, even though we could. But it's easier just to throw the thing away and just reproduce the entire thing from initial state because it is stateless. We have to consider the stateful data. We have to consider all system data in a stateful change, but in this we don't care because we're fully reproducible. Interestingly, the stateful parts of our stack tend to update much less frequently than the stateless versions. In stateful, we're talking about our catalog, we're talking about our data itself, but how we store it and how we format it doesn't change that often, so we don't actually update it very frequently. Whereas this stateless part of our stack, in terms of our processing cluster and in terms of our interactive notebooks, we upgrade all the time because we want to continuously deliver that great user experience for them. And then really everything in stateless, like it's S3, it's security groups, it's these things that don't tend to change, and then for stateless, it's everything else that does this. And I really encourage, like when designing an architecture, whether it's a data-driven system like the one we described here, or just systems in general, to kind of think about, hey, how can we separate stateful and statelessness? Because it makes it so much easier to quickly evolve the portion of the system that can live in the stateless stack. So some of the things that we did is so we run Jupyter Hub on EC2, but all of the user folders, all of the user notebooks are actually stored in S3. We map that S3 drive to that Jupyter Hub instance. That way it keeps things stateless. That clean separation lets us go really quickly, lets us evolve really quickly. And we're making extensive use of Amazon's AWS Cloud Formation in order to do this. Which is, I think, really remarkable. I think it represents a nice approach for building these types of systems. And that rather, typically we might deploy something, when you think about deployment, you might think about, hey, let's write a script and run all our deployments, run the script end to end, and our system would stand up. But we found it best to think about Cloud Formation as more of, you're not building deployment scripts, you're building deployment APIs, where you have a template, which is essentially an API for your system. In our case, we have a clear distinction between our stateful template and our stateless template. And because that's an API, we can automate its deployment through it just like you would any other API. You can plug it into lifecycle or tooling just like you could any other API. And this is, I think, a new but important shift in how we build software is, obviously there's a broad shift to APIs in general, but I think it's interesting that those same advantages, those same patterns, those same properties apply to how we can effectively deploy a system by building APIs to do them. Now let's take a look at how we get data into the system. We talked about how we put it all together. And it's made it pretty simple as we could. So as we talked about earlier, our healthy intent, the vast majority of that is running in Cerner's data center that we've operated for some number of years now. For data that we want to move into AWS, we're basically doing a Hadoop distributed copy. It's basically like a MapReduce job that spins up and does move things over into our S3 buckets. After we copied over there, we load everything into this catalog of data, so our users can easily find it. And then we actually have another use case that I think is interesting, and to make this system collaborative, is that we'll actually selectively syndicate data sets to organizations, to our clients with whom we're working. So our clients may want to do their own deep data analysis from this. And in this, they actually can run in their separate, the distinct AWS accounts, and we'll essentially S3 sync things over into their accounts. We actually build, again, using an API-centric approach, we're building this data syndication service that tracks what can be shared with whom and tracks all the security and the traceability policies behind that. But the mechanism is essentially a sync between accounts. And that way, when our users want to spin up their own system, which can include arbitrary code or arbitrary libraries, so it needs to be strongly isolated, they can do so with the right data, but do so safely. But for the purposes of this talk, for the purpose of this presentation, we're going to zoom in a little bit on the core system of where we're working with the data. And really, the DCP, like we said, starts with a move to Amazon S3. And then we trigger a data pipeline, which if you're used Hadoop for very long, it's a little, you can kind of think maybe a little bit of like an Uzi as a service. There's a lot of differences there, but it can look for events, new data landing in, and then trigger some processing engine that writes out to some end state. And that's what we do. Our ingestion is also written in Apache Spark, running on the Elastic MapReduce cluster. And then the job simply converts data into Parquet, a Parquet file format that lives in S3, and then registers those Parquet files with the catalog. Now, our users never actually know that data is written in Parquet. That's entirely an implementation detail. They work with this catalog, which is really just like a data dictionary. I know a lot of people like to joke that all good ideas come from the 1970s, right? So it's really like this new view of a data dictionary that has better scalability properties. We use the Parquet format because it's a column-based format, so a lot of our query operations are very efficient because they scan entire columns versus a row-wise format in which we have to like go row by row by row for every query that we do. So Parquet is actually an excellent format, and Apache Spark is like natively optimized to speak Parquet. So while this isn't the only option for a data format for this sort of deep analytics use case, it's kind of the incumbent just because of the deep Spark integration with it, and also the integration with libraries like Athena, or toolkits like Amazon Athena and others. All right, we got our data in, we got it in the catalog, and so we kind of got through this architecture piece, and now we face our next set of challenges as we go, and that is dealing with the sheer overwhelming complexity of healthcare data. We talked about the hundreds of distinct sources and all the ontology, all the complexity that we're dealing with, and this is perhaps our biggest essential problem, because complex healthcare data isn't going away. This complexity is here to stay, so how do we deal with this? And to illustrate it, we're telling you thousands of different code values from different systems. Oftentimes, there'll be incomplete or conflicting data. This is the United States, so of course we don't have a common person identifier, so we have to write logic to match people, make sure that two records are actually for the same person. Even when we have standard data models to bring into the system, they're inconsistently interpreted. Like, maybe you can write a great spec, but there's always some room for interpretation in a spec. And as your data system scales big enough, you will run into every possible interpretation of that spec as we go. And that results in we have different meanings. Different things mean different things in different contexts. They have to be reconciled across sources. And, of course, human working memories. 5 to 9 items, so not very good, right? And there's just no way around this. This isn't something, we land in architecture and high-five each other. It's like, yeah, we've nailed the data complexity problem. This is like a systematic approach that we have to work through. So the first thing we've done is taken all of these data sets that we bring in and put it in this data dictionary, this data catalog that has well-defined columns, has well-defined schemas. A lot of times if you've been in the big data, quote-unquote, space, you may have heard like schema on read is like hyped up as this really great thing. And schema on read is a good thing if you don't have a schema, right? If I need to analyze data and there's not a defined schema from my input sources, then yeah, let's use schema on read because at least I can do it. So that's the value there. But given the choice between not having a schema and having a schema, you want a schema, right? So somewhat tongue-in-cheek, I kind of joke that schema on read is a bug and not a feature. Sometimes it's a necessary bug, but that's not where we want to be. So once we have a catalog, then we can start looking at how do we make sense of this complex data itself. And our challenge here is that it becomes the data, this balance between a purely highly faithful representation of a very complex data set and something that can be actually easily used by a user. So a lot of our analysis is actually done on data models that are based on the FHIR standard. And so here, this is actually the FHIR condition model that we've taken the FHIR schema and fully expanded it. So here's the full definition of the FHIR condition model. And it keeps going, and it keeps going. And the crazy thing is that these FHIR-based models, they're designed to hit that like 80% case. They're actually simplified versions as opposed to other healthcare models in which let's get the things that are needed most often, but maybe sometimes we don't, but for the long tail things, for something that I only need a couple % of the time is not in this data model. So it's already fairly well curated, and that's actually one of the reasons we use the FHIR-based data model for a lot of our deep analysis, because there's been so much curation and so much effort in defining what is the important data sets for this analysis, what are the important data elements, what should they look like, and how do we work with it. But because of this all this expressiveness comes with the cost of this complex data model that we see, walking through this schema. So how do we go through this, take this complex data model and make it easier to use, easier to work with? And the pattern that we found that works really well is we can take a really complex data set and we'll just project it onto something much simpler. So we say a SNOMED code, this might meet hypertension medications, this might meet a condition, and then we can project that onto, hey, this person is hypertensive. And what's interesting here is that these projections are lossy, right? There is less information is hypertensive than there is towards the bottom of that. But depending on your use case, oftentimes a lossy projection is fine. In fact, it's actually what you want. If I'm doing some deep analytics of a system, I just want to see, hey, is this person hypertensive? I don't need all this underlying complexity. And so what we found is the ability to take these very large data sets and using this elastic environment in which we're working to be able to create many projections of the data that are much simpler to work with. So for any problem at hand, I can create the projection that I want. I can work with that much simplified data set and do my analysis there. And maybe I can reuse that projection for similar problems. Or if I can't, then I just create another one and do it, which is another advantage, another quite advantage of some of these elastic environments, the ability to have a scalable data catalog that I can contribute new things to without having to pick up the phone and request, hey, we need some more hardware running this system. And so once we have these projections, of course, what's interesting is as we have these simplified projections, they almost always end up looking like spreadsheets. Everyone just wants spreadsheets. They plug directly into every machine learning tool that exists. They plug into every analytic tool. They can export databases. Everyone wants just giant spreadsheets. And just assume all your users want giant spreadsheets, and you'll be in a much better place. So how do we create and just turn things into giant spreadsheets? We found a few patterns that work depending on the use case. One is a rule-based approach for projecting complex data into this giant spreadsheet. And so a rule engine is actually a pretty good way to do it because oftentimes they're very expressive, and they're Turing complete. You can put arbitrary code in there, and also rules tend to avoid spaghetti code in that they don't get quickly twisted up in one another and deal with that sort of thing. So a rule engine is a nice approach, but it requires a pretty savvy user. It's usually a developer that's having to author these rules at a low scale, at a granular level. Another one to solve a similar problem is this emerging spec in healthcare, the clinical quality language specification. And in that it's similar to a rule approach, but it's a more constrained model. So it's not as expressive as you might have from a full rule engine, but it can hit most of your use cases most of the time. And it also benefits from the fact that there's been a lot of work in sort of curating and defining this sort of query language in a way that it's easier to use. And also, interestingly, the quality language is sort of migrating towards using FHIR as its actually core data model. So when it's a medication statement or hypertension or clinical condition or that sort of thing, these are the FHIR resources. So they're really well-defined and well-documented in what they're working with. And then the next one to create these simplified projections of data is something that's much more familiar to a much broader audience, and that's just SQL. Maybe not as expressive, but a lot easier to get into. So this same query that we just saw, find hypertensive patients in the previous one. So might write some SQL where we'll query for everyone from our conditions, for hypertension conditions, and we'll union that with some medication statements that imply standard meds. And the nice thing is that as we write SQL, it's very simple that we can just wrap that and turn it to Spark SQL. So then it runs directly into our Spark cluster. This is actually a valid query that runs in our system today. And everything in here is really standard SQL. The one exception is something that we'll zoom in on. You'll see some helpful user-defined functions like in-value set here that kind of makes it easier, kind of eliminates some of the complexity of this SQL. And once we have these things, once we turn these things into giant spreadsheets, well, we can do things that are really easy, like let's just count our hypertensive patients. There you go. It's a couple lines of code to find all from our spreadsheet view of the system. Or if I want to take that and I want to join it if I want to join to diabetics, for instance, we can join that in hypertensive patients who are also diabetics. There it is right there. Again, a few lines of code. Other things, if I want to look at observation data instead, we can go grab that in this query. Here's our giant spreadsheet. And then we can look at different views of that. So we can compute summary statistics of this sort of thing. I mean, all of this is just following that same pattern. It's like create these projections for a use case and then manipulate them interactively. And of course, this is just simple summary statistics, but I can take that same spreadsheet and there's a view of our distribution of our data. And if, you probably can't see that, but if you let's see on the screen, you might see like some outliers outliving and this sort of thing. So you can get kind of quick, immediate impression of, hey, what does our data look like? I mean, is there something that we need to analyze? And if there are outliers in this, well, then we can just go back to our SQL and zoom in and figure out what's going on there, trace it back to the data sources that we're working with. And all of this is kind of built on these sort of, we'll see like little helper functions like this that are in value set that are embedded in our SQL. And all this is it's just a user-defined function that just looks, hey, is this code value match one of these hypertension value sets? So I have a collection of codes that I believe identify hypertension. Is the code value in this column in my SQL query one of them? And then we'll match it and use it there. And we see this pattern popping up again, where we'll use Spark SQL. We use a collection of user-defined functions to work across these data sets, like in value set. And then we can broadcast reference data to this cluster. This creates a pretty neat experience when working with it. And to sort of illustrate that, I mean, here's just pushing a value set. So we'll create, here's the set of value sets that we believe identify these particular medications. We'll push them to a cluster. In a real example, we'll probably load them from some external publication from the Value Set Authority Center, if you're familiar with that, for instance. And then we can run the SQL in there. And we find ourselves creating many of these. SQL is our interface into this analysis problem, but anything that can't be expressed in SQL, we push into user-defined functions. So in value set is our simplest example, but extract terms right inside of our Spark job, our processing cluster. We can do a natural language processing step in which we extract terminologies right out of the document in that Spark cluster, for instance. Or we could even invoke rules. If there's logic that can't be expressed in SQL directly, we could invoke a rule engine right in our processing job. And this is kind of one of the things that I think makes Spark somewhat unique in terms of, I mean, there's other ways to do it, but one of the compelling advantages of it in that all these functions, it's just Java code. So I have an SQL interface to keep things simple. It's like Alan Kay liked to say, like, simple things should be simple. Well, they are. They're SQL. But complex things should be possible. Well, they are, because we can write these functions that go and do more sophisticated things written in any language that could run on the JVM. And it's fast. So here's our simple query here. An internal cluster, have an internal test cluster with 300 million encounters running just 8 nodes, which is much smaller. Most of our clusters will be bigger than that for their analysis. And this query will come back in about 4 seconds running it. And it takes advantage of that efficient Parquet columnar format that we're working with. So we talked about the toolkits, and we talked about these patterns of creating giant spreadsheets, combining them together and doing analysis. Now we're going to look at applying that to to actually do some applied machine learning tasks. And so if we want to do something like build a predictive model, do something like that, well, we'll just start. Let's just put together these spreadsheets that we want. So first one is that we'll grab some demographic information, put that in our patient spreadsheet. We'll grab some observation information and put that in a spreadsheet. And I'm going to zoom in on part of this query just briefly, because I think this shows like some of the capabilities of doing data engineering at this scale. And this looks complex, but it's really just standard SQL once again. And it's easier. I think it's most easily read from the inside out. So if the code is in this value set for glucose level, we include it in our average. Otherwise, we'd return null, which simply isn't included in the average. And that little bit code computes the average glucose level for that person. Of course, this query as it stands, looks for their average all of history, which probably isn't what we want. So we'll add to our group by clause, we'll include month and year or whatever arbitrary date that we're working with. And then we want to include that in our results table, and we can do that with a bunch of other things as well. So again, we've gone here from that complex but complete Firebase data sets, and we converted it into a much simpler data model that we can interactively explore. And we do it with almost anything. So here's something similar for our conditions. Same exact pattern where we're getting like the onset for these conditions that are used for our data analysis there. Then we can join these tables together, and we land in, again, this view that we can feed directly into our machine learning use case models or other use cases. And back to the collaborative space. Well, we can take our time series, we can save it as a table of all our patient history information, and then we can pick it up from there. So here, whether we use Spark's built-in machine learning capabilities or other systems, other machine learning capabilities, by having it in this sort of tabular form, we can tap into it. Here's a little bit of code that actually, if you're familiar with like scikit-learn or other toolkits in the Python space, should look very familiar. We can take our high-quality data, put it into this pipeline, and build a machine learning model. And this is where we kind of maybe draw the distinction of, we talk about data engineering, which is everything that we've done, like I said, putting everything into giant spreadsheets, and the machine learning use cases, which is picking it up from there. And this line's a little bit blurry, so you can debate where exactly it is, but we'll kind of use this definition for the purposes of our efforts. And we actually are excited because there's actually something that we're sharing. We're actually open sourcing a library today to take all of FHIR data and natively represent it in the Apache Spark project. So the advantages of FHIR being all the curation and efforts that exist in there today, and be able to put that and directly query it with the exact same SQL that we saw there today. It's kind of getting the advantages of Spark data model, of the FHIR data model, and with native support built in for Spark. So if you just go to engineering.cerner.com, it'll be the top blog post right now, and that's actually a link to the project itself. It's Apache licensed, and it's up on GitHub. You can find it all in that sort of thing. And I think this could really help our data engineering use cases for working with these FHIR-based data sets. So that's our data engineering piece, and I think that we also want to look at how this plugs into our machine learning use cases. And when I just talk about turning the world into giant spreadsheets, you might go, well, what does that have to do with machine learning? But what's interesting is like every machine learning job, every machine learning task follows the same basic pattern, whether it's logistic regression or whether it's a neural network. They all follow the same patterns, that the machine learning algorithm has a set of parameters that you give to it. And then it goes through and it finds the optimal combination of those parameters. So the machine learning, the algorithm that's produced, minimizes the difference between what your test data says and what your predictions are. They all follow that same pattern. They're just walking down this slope to find this optimal combination. And by going through these data engineering exercises, by providing these really high quality inputs to our machine learning model, one, it'll make the machine learning model easier, which means it will run much faster, your models will converge much more quickly, and two, you'll get better outcomes because you're taking advantage of some of this human knowledge that we have. There's so much human knowledge in terms of these coding systems and these data models and these data structures. And by taking that, we make machine learning much more effective by giving it these high quality inputs that they're working with. And as an engineer, I kind of think of all this as it's like we're just approximating functions in a way. And we're just basically, there's certain functions that I know how to write, so I can easily write albumin level greater than some range. I don't need machine learning for that. I can write that function. I don't know how to write this function to say, hey, is there something abnormal in this image? Or it doesn't have to be images. Is there something in this data that predicts some outcome that we wouldn't expect? And this is so much of what we do is in terms of, as I view it from a software engineering perspective, is that, hey, there are functions we know how to write, there's functions we don't know how to write. Let's create an environment to create these approximations of functions and continuously improve them, and then integrating them back into our system just like we would any other function that we work with. And it's nice just to have this rich variety of toolkits that can do this sort of thing. Of course, we talked about this deep complexity dealing with all these sorts of things, all the technology, the deep complexity of all the data working with this sort of things. But the theme to go to these simplified views of this data is reproducibility, this ability to go from nothing, from a system that doesn't exist to just data, to be able to land an entire architecture, be able to reproduce an entire data engineering pipeline, to create these projections for the purpose, and to apply machine learning model. That mitigates all this deep complexity that we're dealing with. So if we do one thing, we have these constraints that we really care about. We have our security, we have our user experience demands that we cannot budge on. But in addition to that, the ability to reproduce the systems and iterate quickly on it are really what gets us to these sort of high-level views that plug cleanly into a huge number of analytic tools and machine learning tools and do so really effectively. And this kind of gets us to another sort of positive space, another positive loop that we can work through. and that we have a new question. We have some new need that we want to solve. And by using these patterns, we can model the data for the question at hand. So we can create this projection that meets these needs so I can do this analysis as necessary. We can simulate, we can refine, we can build the model, we can test it, we can validate it. We can analyze the results in that model, and we can feed it back in. So now that we better understand the question, maybe we have another one, or maybe we tweak the parameters of the question and adjust it. And then, of course, through all of this, I mean, we're creating these new data sets that have each one of our transformations, each one of our functions, each one of our data sets has value, and we need to push them back in to this catalog so others can discover them, so they can leverage them, so they can take advantage of them for new needs that emerge. And what's exciting about this cycle is that we can do it on demand. We can do it at scale. And by we can go through the cycle really fast without even having to sort of leave that mental zone of where we're doing this analysis. So if I don't have to go and wander off because my job's going to run for the next 5 hours, if I can stay in that environment and interactively do this analysis, we can go much more quickly. And by going much more quickly, I mean, really that just boils down to the fact that we can innovate more quickly than we could have before. And I think that's probably the most exciting thing about all these patterns that we're working with. So with that, I thank you, everyone, and I do have a little bit of time for questions. No. So I think there are some logistics around the questions that people are going to line up. Guess we can.
I can talk loud.
Okay, well, you go ahead. I'll repeat the question. Why don't you go ahead and
Okay, so thank you very much, number one. I learned a ton. I am very curious. It does seem like with the Spark implementation that you showed, you're requiring a data model to exist using that proverb that you gave, which I thought was pretty good. My question is, if you make that decision to have a data model on top of Spark, why choose Spark over Redshift? Is there any reason?
Yeah, okay, so the question is, so given that, and predicated on this data model, is there a reason to use Spark over something like Redshift? So I think that our approach is like, it depends on the use case. And part of this environment is we want to be able to apply whatever tool fits best for the problem at hand. So if you have a variety of analytics that works really well in a Redshift model or an Athena model, absolutely use those. We used Spark because some of our workloads worked better for one is like we have a variety of pretty rich and complex user-defined functions written in Java that work really well in a Spark cluster, so we could isolate that. So it's a bit of a better use case for our problem at hand. And then and Spark also works really well with a lot more deeply nested structure data sets, which is doable in some of these other platforms as well, but the Spark support is solid for it. But like I said, I mean, I think that part of it is like, maybe the distinction that I draw is like, for things like Redshift, if you have like the same style of queries that you tend to run or same sort of analysis, something like an MPP style database like a Redshift is probably going to beat a Spark because it can be strongly optimized with that schema that you defined. If you want to create some crazy new view based off of a few hundred terabytes of data interactively, Spark tends to do better at that workload if you don't really know what your view of data wants to be. But anyways, I'd suggest trying both and would do whatever works for you. See a hand back, sure thing. See a hand back there.
So do you ever have a use case where you need to completely remove data in your data lake?
Yeah.
Because some sort of compliance reason? And Parquet is a pin-only format.
Right.
You can't do updates, you can't
Yep.
How do you handle that?
Yeah. So the question is like we have to delete data from our database, but a Parquet you can't delete from a Parquet file. And I think that the thing is there's like every data set that we have in this is something that we can reproduce from the initial raw data source. So what we do is we don't attempt to remove from Parquet. We'll just delete the Parquet file, and then we'll recreate it from, we'll delete the Parquet file. We'll go back to the raw data format that comes in, which could be anything ranging from a CSV to whatever import we got from the system. And so we'll actually recreate our entire data set from scratch, quote unquote, without that data. But yeah, it's a big challenge in this type of system. So you have to be real. But this is another case where like strong reproducibility of your data sets is really, really important. That's a good question. I saw one go up there, then I'll get to you. Yes, go ahead.
Question about your use of AWS data pipeline.
Mm-hmm.
This is not a HIPAA eligible service, but if you had to use that for
Yeah. Yeah, so the question is data pipeline, and the fact that data pipeline isn't HIPAA eligible. So we use data pipeline in a very narrow sense in such a way that it never sees any actual data. And so basically, and this is a lengthy conversation we had with our colleagues at Amazon as well to make sure that we were well covered in this case. But the way we use AWS data pipeline is that it basically looks for the presence of a success file, like, hey, there's some data ready to process, and then it goes and launches a Spark job running an EMR that does all the workload. So the EMR cluster is HIPAA compliant. So yeah, basically we use it as basically a way to trigger jobs that run in a HIPAA compliant environment. Yeah, that one was, we worked through that one, but yeah, we made sure that we were covered there. And I saw up here.
Do you have any situations where the data scientists take out the data in Excel spreadsheets, image the content, and push it back in, do some data enrichment jobs on the fly?
Yeah, so they take out the data into an Excel spreadsheet and do some other manipulation there. So we actually have a number of use cases in which we'll convert some summaries data into an Excel and then can do some manipulation there and then push that back in for reporting. I mean, the ones that we use largely now are just like some summary statistics and that sort of thing. Because our data sets tend to be much bigger than you can practically fit into Excel. But when we do it, it tends to be just like general broad population counts and that sort of thing that we do that with. So we have a little more flexibility there since there's no PHI or PII in those spreadsheets that we're dealing with. All right, so got a few more minutes. And yes, sir.
How do you kind of agree on the logic of those projections? It sounds like it's from a data engineering point.
Yeah.
Obviously, the person wants to name on it.
Right. So the question is, how do you agree on the logic of those projections, what they should look like? And honestly, I think that the way the system evolved, I think was because of challenges in that very question. Like it was difficult. Building any projection that's suitable for one use case is probably not suitable for another. So what we've kind of done here is we've let our data scientists create their own custom projections very frequently and then share projections with one another whenever it makes sense to do so. So it's sort of a collaborative approach where and sharing is often in terms of just, oh, here's my SQL query, or maybe I write my projection back to the database, back to the data catalog, and you can pick it up from there. I think I'm in a way I'm kind of like doing an end around of your question by saying, hey, we don't have a ton of shared projections, but we kind of let people create their own ad hoc and customize it. I will say that as we're evolving this system, we are seeing some commonality that tends to show up again and again and again and again in these projections. So we're actually working on taking that commonality and refactoring it, having a small number of sort of common projections that a lot of people can use. Kind of similarly to how Fire chose, here's the data elements to include and exclude. So we want to find some common projections that will meet the 80% case. But that's a very iterative, constantly getting feedback, when do we need things sort of thing. I don't know of a good shortcut to finding good common projections other than just make it easy for people to create and make it easy for people to iterate on. It's a real challenge. All right, so maybe one more question. All right. Okay, last question. Yes, sir. Sorry, I couldn't see over there.
Spreadsheets are great, but what about electroencephalographic data that lends itself to time series databases? Or what about many of the other forms of data? We're just not talking about clinical data.
Yeah.
We're talking about lots of other different types of heterogeneous, unstructured data.
Yeah. So the question is, spreadsheets are great, but there's a lot of stuff that doesn't fit into spreadsheets, right? So one is I'm being a little bit tongue-in-cheek when I say spreadsheet. So I call it anything that could fit in a tabular form works really well. So that hits part of what you're hitting there, but obviously not all of it. So EKG data or time series data can fit in a tabular form, and that works. We actually use time series data extensively using this model. So for unstructured data, that can get a lot more challenging. So a lot of times what we'll do for unstructured data, so if you have images or something that, depending on the size of it, you can kind of sort of have maybe what you consider a sort of a degenerative form of a table where you just have one column and it's just the unstructured data. Then you have to write very customized code to deal with that. The system that this pattern that we're describing here doesn't solve the unstructured data use cases. I mean, it basically lets us makes it working with simple data simple. The one piece that we do quite a bit of is that when dealing with unstructured data, a lot of times you'll run through like some very complex like feature extraction algorithm against whatever clinical note. And then once you have run that feature extraction algorithm, then you could put that in a spreadsheet. You can like have a list of vectors. Again, I'm being a little bit tongue-in-cheek about the definition of spreadsheet. But yeah, there's a ton of problems that aren't fit in this pattern. But what we found that we do is like we write complex logic when you need to, and then when it makes sense, project that onto the simpler form, which may just be just feature vectors or term vectors or n-grams or sort of thing if you're grabbing stuff out of unstructured content. And of course, the right answer to that is going to vary tremendously depending on the domain space. So all right, I've been kicked off the stage. So hey, thanks again, everyone. I appreciate it.